What is stability in open and closed-loop control systems? Imagine you're riding a bicycle. If you lean a little to one side, you want the bike to straighten itself out and keep you balanced. That's a simple way to think about stability in control systems. In electrical engineering, stability means that when you give a system a little push, it doesn't go wild or keep oscillating forever. Instead, it settles down and stays within predictable limits. In an open-loop control system, there's no feedback to correct what's happening. Think of a washing machine that runs for a set time regardless of how clean the clothes are. Its stability depends on how it was built. If the machine's parts respond naturally without causing runaway behavior, it's stable. But if something changes, like the load size, the system might not handle it well and could become unstable. Open-loop systems are more sensitive to disturbances because they don't have a way to adjust on the fly. Now, in a closed-loop control system, there's feedback. It's like a thermostat that checks the room temperature and adjusts the heater accordingly. If the room gets too cold, the thermostat signals the heater to turn on more. If it gets too hot, it turns off the heater. Stability here depends on how well the feedback works. The system is stable if all the roots of the characteristic equation, which is a math way of describing the system's behavior, have negative real parts. That means the response will die down over time and not blow up or oscillate endlessly. Mathematically, the closed-loop transfer function is written as the plant transfer function divided by 1 plus the product of the plant and feedback transfer functions. The characteristic equation is 1 plus that product equals 0. If any of the roots, called poles, have positive real parts, the system becomes unstable. If all roots have negative real parts, the system remains stable. In real-world electrical engineering, making sure a control system is stable is key. When designing controllers like proportional integral derivative controllers, engineers tune the parameters so the system responds quickly but doesn't overshoot or oscillate. This balance keeps the system safe and reliable. To sum up, open-loop stability depends on the system's natural behavior without feedback. Closed-loop stability depends on how the feedback and the system work together, requiring all roots to be in the left half of the complex plane. Stability ensures the output stays within bounds when the input is bounded, which is essential for safe and predictable operation in electrical control systems.